In section 3.7, we're going to talk about optimization of a function. Now, we've already done optimization in prior sections. Remember, anytime we find the extrema of a function, in a way we are optimizing the function. Now, there are different types of optimization problems. The kind of optimization we do in this course, which is the calculus course, are the kind of optimization that require or involves derivatives, whether we do first derivative or second derivative test for extrema. There are also another kind of optimization which is called constraint optimization, which is done typically in a course in linear programming. So we're talking about the first type. Now, when it comes to finding the extremas, we've already done that throughout previous sections. If you recall, we had a couple of theorems. We had Fermat's theorem and extreme value theorems over a closed interval, which guaranteed pretty much the existence of an extrema. So the difference now is with applications that we're looking at, we may not have a closed interval. Okay, so when optimizations take place over an open interval, then the problem may not have a solution. Okay, so that's what we want to investigate in this section, whether these applications have solutions. And we're going to look at, again, a lot of word problems. That's all there is in this section. They're all word problems. So let's begin by first looking at the guideline here that we have right in here. These are the guidelines for finding the extrema of a continuous function. Now notice we have over an arbitrary interval. It's not over a closed interval here. So the guideline goes, suppose we have a continuous function with only one critical number. So that's important. We got to have only one critical number. Okay. And when there's only one critical number, then let me get my pen going here. Okay. With only one critical number inside the interval, then we can do either first or second derivative test to find the relative extrema of the function at that point, at C. And if indeed there is a relative extrema at C, then that turns out to be also the absolute or global extrema over the interval. And the reason is because there's only one critical number. That's why. So that's the guide. So we're going to end up doing first, second derivative tests in this section for most parts. Now, when it comes to solving these word problems, these optimization problems, they're all going to be word problems. Again, these are the general guidelines. Just like with any word problems, we need to declare the variables, right? So step one here that's what exactly it does. It declares the variables of the question. And of course, we cannot divorce geometry from mathematics. Everything we do is it's just better when we draw a sketch, right? Or a figure if we can. And number two is actually the challenging part of this process, finding a mathematical expression for the quantity to be maximized or minimized. That's the key. That's the equation, actually, the function that we want to optimize. And usually we get that by, of course, looking at the inner relationship between the variables in the word problem or application. And then we're going to be given some set of conditions most likely, and then we just incorporate those conditions into our work. So the condition given, we're going to use them to express quantity to be optimized as a function of one variable. Oftentimes, as you will see, as we go through this process, you will see we may have several variables. And because we only handle single variables, therefore, what we need to do is we need to simply express these in terms of these several variables in terms of a single variable to be optimized. Okay. And of course, when all of that is done, then we can actually go through the optimization process. Okay. Then we have a function of one variable, and that's easy to optimize. So those are again the general guidelines. Remember, the key is to come up with the equation that we want to optimize, or the function actually we want to optimize. So let's take a look at this first example. In this example, the question reads, the sum of a positive number and its reciprocal is to be as small as possible. What is the number? Okay, so for example, I'm just making up a number. Let's say my number x is 15. I'm not saying that's the answer. I'm just going to find the number. So 10 is the number. The sum of a positive number and its reciprocal. Well, the reciprocal, call it 1 over 10. So right now I have 10 plus 1/10, so that's 10.1. Okay, that's what that means. We want this sum to be as small as possible. So let me make up another one. Let's say I have 20. Its reciprocal, 1/10, so it's going to be 1 over 20, so it's going to be 20.05. So notice the number is getting bigger. So if I go, let's say the number is 4 plus its reciprocal, 4 1/4, 4.25, so it's getting smaller. So that's essentially what we want to do though. But we don't want to guess at these numbers, right? We want to find them algebraically. So let's begin. The fact that the number is positive tells me x is greater than 0, and the sum of a number and its reciprocal. So what we want to do is we want to minimize. To optimize is to maximize or minimize. In this case, we want to find the minimum, right? Because we want this sum to be as small as possible. So we want to minimize a function. What is this function? A function of x. Well, it's going to be the sum function, right? The sum of a positive number. A positive number, we call that x. So that's x. The sum of its reciprocal is 1 over x. Right? So there we pretty much dissect the word problem. And it's going to be 1 over x. Now, we want to minimize this. F prime of x, we're going to go through our process. Well, for us to find the extreme of a function, we're going to use first or second derivative tests here, right? So I'm going to do f prime x, which is going to be 1. The derivative of 1 over x, again, that's x to negative 1. This derivative is going to be negative 1 over x squared, right? And that's the derivative, negative 1 over x squared. And because we want to find the critical numbers of the function, therefore I need to simplify this derivative by combining the 1 and the fraction. And now I can factor this. Remember, we need to simplify all derivatives because the way we find the critical numbers. Now, and it's right in here. F prime of x is 0 or f prime does not exist, right? Those are then that's how we define critical numbers of a function. Places where the derivative either is 0 or does not exist. Now this derivative doesn't exist when x is 0. At x is 0, the derivative does not exist. Now the domain of the function, by the way, is positive values, right? So 0 isn't in there anyhow. But nevertheless, that's the critical number. The numerator, we set it equal to 0, x minus 1, x plus 1 equals 0. So we'll pick up two critical numbers, plus minus 1, from that. So if we actually go through our first derivative test now, here's f prime. This is 0, where the derivative does not exist. And here's 1, here's negative 1. I'm just going through our routine, optimizing the function. And our first derivative test, that is. Then again, pick a test point. So for example, let's say I pick 3 here. Plug it into the derivative function. So with 3 minus 1 is positive. 3 plus 1 positive, divided by 3 squared positive. So that ratio is positive. And then you can try different test points. So for example, at 1/2 again. In the numerator, first factor is negative, second positive. Denominator is always positive because it's a squared. So that's going to be a negative ratio. And so on. And I can see that this one will alternate. Okay, now remember our function actually is going to be a positive, right? Our domain was positive. There you go. So that's what we're looking at, right? We're looking at over that segment of the number line from 0 to infinity. All right. And you have decreasing, you have increasing. Therefore, there's a local minimum here. Now, again, because there's only one critical number over this interval, therefore, this is going to be the absolute. And what we mean by that is this. There's not going to be, let's say, another number out here that's going to be minimum when you add the number and it's reciprocal. This is the minimum, the absolute, the global minimum. Okay, so we have, we're going to call it now absolute because there's only one critical number over the entire domain. So it's absolute minimum, and the minimum is going to be f at 1. Notice the value of the function at 1, which is 1 plus its reciprocal. So 2 is actually the minimum total that you're going to get is 2. Okay, and that's when x is 1. And there we have it. Now, here the other way we could have done this is once we found our first derivative, let's actually find our second derivative of x, because we haven't done that. Now, our first derivative, again, remember f prime of x was 1 minus 1 over x squared, right? So if double prime is going to be derivative of, which is 1 minus x to negative 2. It's going to be negative of negative 2 x to negative 3 or 2 over x cubed. Derivative of 1, of course, is 0. That's why. So we have 2 over x cubed. Now, this function, the second derivative function, is always going to be positive, right? Always positive. That's going to be positive when x is equal to 1, right? So this way also we can establish that we have a local min. This is our second derivative test that I just did. Right, for second derivative test, you find the second derivative and then you try the critical numbers of first derivative in this function. And if it's positive, then you have a local min, the second derivative that is. You have a local min, and if it's negative, you have a local max. Remember, positive means the concavity is upward, positive. This is f double prime positive. And negative means this is f double prime negative, means concavity, down concavity. This is positive. So we have a minimum. If it was negative, then the peak would be the max. Okay. And there you go. We're done with this exercise. Okay, let's take a look at this problem. This is exercise number 8. The question reads, the owner of the Rancho Grande has 3,000 yards of fencing with which to enclose a rectangular piece of grazing land situated along the straight portion of a river. If fencing isn't required along the river, what are the dimensions of the largest area he can enclose, and what is the area? Okay, so let's take a look at this one. So clearly in this case, because we want to find the largest area, right? The largest area. So Looks like in this case the optimization of the function involves finding the maximum. True? So here the word optimize means maximize. So we want to find, that's what we want to do. We want to know what is the max area, right? Now we know the area of a rectangle is x times y, length times width, right? So I can call this, for example, one side is x, that side is x, and the other side is y. It doesn't matter whether it's the shorter side or the longer side. What's important is that you have two equal sides, right? So the widths are the same, and because straight river doesn't matter here, whether even if it's not straight rivers, it does matter. It doesn't matter, it's a straight. The reason it says a straight river is because then these two sides will be equal. Otherwise, if it sits like that, then the sides are not equal, right? So that's why it's got to be straight river. Okay, so notice that our area right now, let me rewrite this. Area, the way I have it, is a function of x and y. So we came up with our original equation. Now our next step usually, and this is important when we get to more complicated exercises. So you come up with the first equation. This is our key equation that we need, that generates the function, creates the function. Now the trouble is that we have a function of two variables. We need to write these functions in terms of one variable, a single variable. So that is either in terms of just x or y, right? And remember, in this case, I'm going to let x be the width. So let's see, the other piece of information we have is this. He has 3,000 yards of fencing to enclose the region, right? Well, the 3,000 yards of fencing involves let's see, that involves actually creating a side, right, a longer side of the fence, and then this other side of the fence and the other side to enclose the region. So that's how he's going to spend his 3,000 yards of fencing, right? So I can say that the perimeter, therefore, which is made up of 2x plus y, should equal to 3,000, right? Now, if I solve for y here, it's easier of the two to solve for, otherwise I can get into fractions. You gotta divide by 2 to solve for x, so we don't want to do that. And there you go. So I'm able to write y in terms of x. Okay, now when we write y in terms of x, now I can write area as just a function of x. That's going to be x times y, but then y, we just said it's 3,000 minus 2x. Again, that equation, this equation came from the perimeter of a rectangle. And of course, this side, right, the side that's attached to the river bank here, there's not going to be a fencing there. There's no fencing there. Okay. And let's see. So what we want to do next? Now we want to optimize this function. Okay, so I'm just going to write this as 3,000x negative 2x squared. Okay. And now to optimize our functions, remember we do it through first, second derivative test. So I need to find a prime. The first derivative as a function of x is, notice you can use a for area or f for the function. I'm using descriptive name a to stand for area. So that's 3,000 minus 4x. Then we're going to set it equal to 0. Okay, to find the critical numbers of it. The derivative function is polynomial, so it's always defined. Therefore, there's another place where the derivative is undefined. And then we can solve this for x. So 4x is 3,000, so x must be 750 feet. Now, we need to decide, just because we have a critical number, by the way, I'm not going to say, oh, there you go, that's the answer. Right, we're not done with this. We have to go through the process. So this is, let's say, my first derivative, f prime, And remember the sign chart we're creating, and suppose this is 750, here is 0. Now again, for this one, because we're talking about geometry, so x has to be positive, right? We can't have negative x values. So we're only focused on positive x values. Now 750 is the only critical number here. So if we get that to become an extrema, then therefore it's going to be a global or an absolute max or minimum extrema, that is. So we're going to pick a test point, like, I don't know, small number, and we're going to the derivative function. So for example, let x be 5. 3000 minus 20 is positive. And beyond 750, choose 800. 3000 minus 800 times 4 makes it negative. So the function increase, the function decrease. So we do have, just out of habit, we write L max, but again, because it's the only critical number over the entire domain for this exercise, therefore this is the absolute, right? So we have, again, I'm going to change the local to absolute max, and the absolute max is going to be at x equals 750 feet. So what is the maximum value? Well, at that point, remember y is 3000 minus 2x, so that means 3000 minus 2 times 750, which is 1500. So the length of that fence must be 1,500 feet, and the width, the two widths, one on either side of it, will be 750 each. What's the area at that? The area at 750 is going to be x times y, correct? X times y, which is 750 times 1500. And that's going to be, what, 1,125,000 square feet. Okay, and there you have it. So it's a pretty reasonable area, huh? Again, if we go through second derivative, just to show you second derivative test for our second derivative test. We were done with the exercise. I'm just going to show you an alternative way of doing it. If I do second derivative of the function, that would be a double prime of x. Well, a prime x is 3000 minus 4x. So a double prime x is just going to be negative 4, right? Now negative 4 here, which is always negative, right? Because it's constant. So remember, the second derivative here is negative. That means the function is concave down, right? It bends away from the tangent line in a negative direction, and therefore it creates a max, right? And that's what we have. Therefore, because the second derivative is negative 4, which is less than 0, therefore we have a local max at that point. Okay, and there you go. That's the answer to this exercise. Let's take a look at another one. Okay, let's take a look at exercise number 20 next. Okay, in exercise number 20, the question reads, find dimensions of the shaded region so that its area is maximized. So the optimization here is, of course, maximization. So we want to maximize the area. Now, in order to maximize the area, again, I need to come up with a function that represents the area. Now, for a trapezoid, I know not everybody just happens to have these memorized, but for a trapezoid like this, if I call this like base 1, base 2, and this would be the height of that trapezoid, or its altitude, then the area of a trapezoid is given by the average base 1 plus base 2. You average the base multiplied by height. Okay, so that's what the formula for the area is. Now, if you look at the one we are working with right now, so the base, the lower base is this one. That's 6 units, right? So that's 6 wide, if you will. And what about the other base, which is right here? Notice the longer base starts from -3, ends at 3. It's, in other words, it's got to be the one base has to be on the x-axis, going from one end to the other end of the half circle, semicircle. Now, the other part of it, because again, depending on where you draw this trapezoid, you see that? Depending on where the trapezoid is drawn, I don't need that line. There, if I draw my trapezoid like this, it's the same base, 6 down here, the longer base, but the shorter base now is different, right? See, it's now this much versus this much. So at any given point, for any other base, I should say, it depends on where the x value is, right? So this is what we're going to do then. We're going to go ahead and write this as the following. So I'm going to call this point x comma y. Okay, that's the point x comma y. And we can write now area as a function of x and y, right? As a function of x and y. So what is it going to be? It's going to be 1/2. The longer base is always 6, plus the shorter base, which is going to be, there you go, that distance, isn't that x? And of course, because you have the entire length of that base, so it's going to be another x. So 2x is the length of that base. And if x, in this case, notice, by the way, x and y are positive. Okay, because there are dimensions, because we're talking geometry, so we're going to choose those to be positive. Okay, and more specifically, our x here, there you go, because we stated this other part of the base based on x. So our x, therefore, let me make it more specific. X is actually going to be between 0 and 3. Okay, so that way twice x makes sense and it will be positive. Okay, and there we have it. Now, let's see, I can actually factor a 2. That's going to be x plus 3 divided by 2. It worked out nicely. Okay, so it's a simple function. And of course, times y. I dropped a y here, right? Times y. So let me go to the beginning of this line. Area as a function of xy, therefore is going to be y times x plus 3. And remember, all our functions must be in terms of just x or just y. So, and we are given the equation for y, right? The equation of a half circle. So that's going to be square root of 9 minus x squared times x plus 3. And then with that, we can go to our routine. And of course, at this point, this is a function of x only, right? So we started with a function of xy, we ended up with a function of x. Now, a prime of x is going to be, we're going to use the product rule, right? So it's going to be derivative of first function, which is 1/2, 9 minus x squared to negative a half times negative 2x, right? Times second plus first times derivative of the binomial, derivative of second. There. Now when we do this work, the 2's come out, and I'm going to write this first. So I have 9 minus x squared first, and then minus, because of the negative here, right? Minus, I'm going to write the other one as x plus 3 over square root of 9 minus x squared, right? That's what that is. Now we need to combine these into 1, so the LCD is the square root of 9 minus x squared. So I'm going to multiply this fraction top bottom by this square root, right? So I can combine them. When you multiply top bottom by the square root of 9 minus x squared, in the numerator we just get 9 minus x squared, because it's being multiplied by itself. Minus x minus 3. Distribute the sign over. Now, I can factor a negative here and combine like terms. There's a couple of numbers there. 9 minus 3 is 6, so it's going to be x squared plus x minus 6 once I once I combine the numbers, right? And let's see, just to make sure I did this right. Okay, I see. Yeah, the x here, that x that there, I need to multiply this times x. Okay, I'm sure most of you caught that. So that means this is going to be 9 minus x squared, negative x squared, and then negative 3x. That's better. And that's going to be negative 2x squared minus 3x. Right? You have negative 3x, and then of course negative 9. Now it's better. Okay, so that's our derivative. Now, if we set this equal to 0, a prime x, we have to find the critical numbers, right? Set it equal to 0, and that means 2x squared negative 3x minus 9 is 0, right? Don't worry about the negative in front, because we can always divide both sides. Once we set it equal to 0, divide that out. Now this should be factorable, 2x and x, and the numbers, how about 3 and 9, but let me go negative 3 here, works better. Negative 3 and 3. So when you FOIL it, you get 2x squared negative 9, that works. And then the OI part of FOIL, that's positive 6 negative 3. Yeah, that should work. Oh, hold on. 9 minus x squared, negative x squared, negative 3x. Yeah, this should be positive, because I factored negative. That's why. There's positive. Okay, this should work. Equal to 0. And then from this, we will pick up a couple of critical numbers, 3/2 and negative 3, right? Okay. Now remember, our domain is between 0 and 3, so we only have one critical number over the domain. But this is what we have so far. We found negative 3, and let's say this is a number line 0. This would be 3/2. Okay, and our domain is right there from 0 to 3. True? So don't worry about this part of the number line. But if I choose my test points, let's say between negative 3 and 3/2, like right in here, pick 1/2. 1/2, so in here, 2 times 1/2 is 1 minus 3 is negative, and 1/2 plus that is positive, and of course a prime was that. So it's gonna be gotta be careful here. Let me actually do this. I'm gonna plug it into this one. Okay, so plug in 1/2 in there, so we have negative of the denominator is going to be positive always, right? We're going to get a number here, but because this is a square root, it's going to be positive. The principal root is always positive. And in the numerator, when you plug in 1/2, you're going to get 1 plus 3/2 minus 9. So that's going to be negative. Negative of a negative is positive. Now beyond 3/2, I'm going to try let's say 2 right in here, plug in a 2. So we have negative of, denominator was positive. 2 squared, 4 times 2, 8 plus 3 times 2, 6 minus 9. Now that's going to be positive. Negative times positive over positive will be negative. Okay, so we have that done. So this is our sign chart for A prime, right? A prime x. So we go from positive to negative, therefore there's going to be a local max, and of course, again, because that's the only critical number over the entire domain, in this case the domain, the sensible domain, 0 to 3. Okay, so I'm just going to call it the absolute max is going to be at x equals 3/2. Now at that point, what is y? Remember, y is equal to square root of 9 minus x squared, right? So it's going to be 9 minus 3/2 squared, which is 9/4. 9 minus 9/4, right? 3/2 squared. That's going to be 36 minus 9, 27. Root 27/2. Okay, now root 27, that's 3 times 9, so I can write it as 3 root 3 divided by 2. Perfect. So the maximum happens again at point x is 3/2, y 3 root 3 over 2. So the question again asks about, what did they ask specifically? They said find the dimensions of shaded area or shaded region. So the dimensions are therefore so let's call it one base is going to be 3, right? Remember, that's this one, 3. The longer base is 6, which lies on the x-axis, right? B1 3, B2 6, and of course the height, called it h, was 3 root 3 divided by 2, and that's the height. Okay, now they didn't ask for the maximum area, but we can find the maximum area if you want. You got the dimensions of the trapezoids. Now let me do the second derivative on this, just because we practice with second derivative tests. And the first derivative, of course, is circled right up here, right? So we're going to take derivative of the first derivative. So that is the derivative of, let me rewrite the derivative here so I have it for reference. Negative 2x squared plus 3x minus 9 divided by 9 minus x squared. Okay, now the derivative of this itself is going to be, I'm going to square the denominator, so it's just going to be 9 minus x squared, and then repeat the denominator times derivative of the numerator. And of course it's negative, right? So let's keep the negative outside as a factor. There you go. So we're going to keep that negative on the outside. And the derivative of the numerator is going to be 4x plus 3, of course, and then minus, that's because of the quotient rule, right, minus the numerator, which is 2x squared plus 3x minus 9 times derivative of the denominator, which is going to be negative 2x, chain rule inside, divided by 2 root 9 minus x squared. Okay, I'm thinking the derivative of root x, or let me actually go u. That's going to be 1/2 u to negative 1/2, which is 1 over 2 rad u. So that's how I got the 2 here and the square root. And the reason it's not 1 in the numerator of this fraction is because of chain rule of what's inside, right? Okay, now let me clean this part up a little bit more. So we have the negative in front. In the numerator, let's multiply top bottom. Let's multiply the top and the bottom by square root of the 2's cross out there. Good. Square root of 9 minus x squared. So that way we get rid of the complex fraction. Okay. Now doing so, when we distribute root 9 minus x squared times root 9 minus x squared, that's just 9 minus x squared times 4x plus 3 minus in the distribution we're going to lose the radicals here, so that's just going to be x times these, so that's going to be negative 2x cubed, negative 3x squared, positive 9x. Looks like I may have to FOIL. Yeah, I have to FOIL in the numerator. The denominator becomes 9 minus x squared, right? Times the square root of that, so it's 9 minus x squared. Okay, 3 halves. Okay. Now, what else can we do here? What else? Let's see. I'm gonna FOIL this. Actually, I just realized I need to also distribute the x over here, which I did, and then the negative sign, right? Negative times negative is positives, which makes all of these opposite what they are. Yep. Okay, so anyway, let me not pursue this further. You can see this can get more complicated, but anyway, this is another alternative using second derivative test to do what we just did up here. So first derivative test was a lot easier. So anyway, so on. Let's take a look at another exercise here. Let's take a look at exercise number 36. In exercise number 36, the question reads: the cross section of a drain is a trapezoid as shown in the figure. The sides and the bottom of the trapezoid each have length 5 feet. Determine the angle theta such that the drain will have a maximal cross-sectional area. Okay. So the effective area that they're actually talking about, the trapezoidal, is right in here. This is the trapezoidal area that they're talking about right there. Okay, so we want to maximize that area. We need to find the angle theta that maximizes that the flow area, if you will. Okay, so let me actually draw this on the side here. So we're going to look at this a little closer. Here's the angle theta, right? Now we're told that right in here is 5 feet, right? Hold on. Let me erase those. Okay, so we're told again the side and the bottom of the trapezoid each have length 5 feet, the sides and the bottom. So that means this is the side and this would be the bottom. Okay, those are 5 each. Okay, so I'm gonna draw this triangle. That's 5, and this would be 5 also. And of course the trapezoid that we want, this is 5. Okay, now we can actually determine let me do this. I can actually determine the trapezoid this way. Okay, and of course this is the angle theta. So I'm looking at this side now. All right. And let's see, let's call this X, right? This is X. And of course, this is the base, right, of the trapezoid. That's this base right in here. And that's going to be 5 feet. Okay, we're given that is 5 feet. Now we need to determine the other base. And of course the height is 5, right? Actually, that is not 5 because these are actually allowed to change. I see. Okay. The 5 feet is this right in here. That is 5. Okay. I think that would be the correct depiction of what's going on here. Alrighty. Because we were told again the sides and the bottom of the trapezoid each have length 5 feet. This is the side, and here's the other side. And the bottom is 5 feet. Okay, that looks better now. Okay, so we need to determine X and call this, call this X1, X2. And by symmetry, those are going to be the same, right? So the entire trapezoid, we need to find the side, right? And we need to find the height of that trapezoid, and then we can determine the area of flow. So we need to determine the angle theta that will maximize the area of a trapezoid. Okay, so we can actually write our equations now. So what is the equation of this trapezoid? Okay, the equation for the area. The area is going to be, well, it's going to be this shaded region, right? And which is the same as the other shaded region plus what's in between, right? That's the area, the flow area, that is. Now, how do I find the area of the triangular portions? So if I look at now the triangle here, this is theta, so this would be theta because you have two parallel lines crossed by a transversal like that. Okay, now we're given that's 5. Okay, here's X, there's Y. So we can now actually determine these. So Y is going to be, if I look at the angle theta, sine of theta is the ratio of opposite to hypotenuse. True? So Y is going to be 5 sine theta. Okay, that's what Y is. Now what about X? Well, cosine of theta is going to be adjacent, which is side X over the hypotenuse. So from this we get X is 5 cosine theta. Okay, now the area of the triangle, therefore, because there's 2 of them, so I'm just going to go twice, let's see, so it's going to be 2 times base times height. Well, base is like x1 times y, right? Now x1 and x2 are equal here by symmetry. Okay, so that's why I can go twice x1 times y plus the area of the rectangular portion, which is what, it's 5, right? And this is 5, right? 5 times height, 5 times y. Now, area in terms of x and y are given, therefore let's now write those in terms of theta. We want area in terms of theta because we want to optimize the angle theta. So that's going to be 2 times x, which is 5 cosine theta. Oh, and it's the area is half base times height, isn't it? Okay, so it's going to be 2 times 1/2. The 1/2 base height, that's the area of a triangle. Twice that because there are 2 triangles. So this is just going to be x times y, which is 5 cosine theta, times y, which is 5 sine theta. Okay. plus 5 times y, that's 5 times, again, 5 sine theta. Make my 5 look like S. Okay. And what do we do next? Let's see, 5 times 5, 25. We can factor 25 out, right? And this is going to be cosine theta, sine theta, plus sine theta. Okay. Now, the measure of angle theta here, of course, this angle is going to be, the lowest it can be is if actually it's wide open. So that's where theta is 0. So this side actually, if it's flattened, which I don't think it can do that, because if it does, then this side will disappear and you don't have a trapezoid, right? So theta is going to be between 0. We're going to make theta greater than 0, and again, the same thing, pi over 2. The max it can get is pi over 2, right? So we're going to get something like this. It's going to look like a gutter there. So we're going to go theta 0 to pi over 2. Okay, and so that's the limits on theta. Now, what else do we need? Let's see. We're good with this one. Now we can actually go through our derivative. The derivative of a with respect to theta is 25. Now, let's see. Cosine theta, sine theta. We can use the product rule here. So that's going to be, actually, yeah, that's fine. I was going to say you can factor sine theta and go 1 plus cosine theta, but then you still have to do the product rule there anyway, so might as well do it now. So cosine theta, that's negative sine theta times sine theta. That's derivative of first by second plus first times derivative of second plus derivative of sine, which is cosine. So this will be 25, and so we have negative sine squared theta plus cosine squared theta plus cosine theta. Okay, so that's the derivative. Now, remember, to find critical numbers of this, we need to set it equal to 0 or places where it's undefined. Well, sine, cosine are both defined over all real numbers, right? So the derivative will always be defined. We just need to find the critical numbers of it. And to do that, we are about to set it equal to 0. There. Now, usually we simplify the derivatives, right? So when we solve the equation, it's easy to solve. Well, in this case, because I see more cosine than sine, let's change our sine squared using the Pythagorean identity. That's going to be cosine squared minus 1. The reason, because it's negative. If that was positive, I would write 1 minus sine squared, 1 minus cosine squared, plus cosine squared theta plus cosine of theta. Okay, and what happens next? Next, I can actually combine cosines. So I get 2 cosine squared theta plus cosine theta minus 1 equals 0, right? Now, the quadratic here, that is hopefully factorable, equals 0, so I'm going to go cosine, cosine, right? Cosine, cosine, and then let's go minus 1, plus 1. Okay. And by 0 factor, cosine theta could be 1, or cosine theta could be negative 1, right? When we set it equal to 0, and let's see. Actually, there's 2 cosine, right? So I'm going to go 2 cosine theta minus 1. That's 2 cosine squared. That's negative 1. And yeah, that would do. So I actually get 1/2 here. Okay, the other one is right. Now, cosine theta equals 1/2. Well, in 0 to pi over 2, cosine of 60 degrees, right? So theta by inspection is going to be pi over 3. Cosine theta equals -1. Well, that's going to be theta equals pi, right? But pi is not in our restricted domain, 0 to pi over 2. Okay, so only the 60 degrees is in there. So this is the only critical number. Notice for this we only have to have one critical number, and we do. So we can go through our first derivative test again. This would be 0 to pi over 2, and this is pi over 3. So we can pick a test point like pi over, and we're looking at the derivative, right? Yeah. This is our derivative. Where is it? Right in here. So we can go through 25 cosine sine plus sine. Okay. Let me write it. 25 cosine sine plus sine theta. That's what we have. So we're going to go in this with, let's say, pi over 6, 30 degrees. So cosine of 30. Now we're in the first quadrant, right? So this is going to be positive, right? Cosine is positive times positive plus positive. So that's going to be positive, right? Because those are all positive. And now between pi over 3 and pi over 2, that's between 60 and 90 degrees. We can pick something, let's see, this is like 60 degrees, which is pi over 3. And this is 90 degrees. So we can pick something like 70 degrees and then plug it into this and see what happens. I'm going to try that, and then I'm going to try to do it using second derivative test. That might be a little easier for this one. Actually, let me go back here. The derivative, this was the area. The derivative is actually, this is our derivative when I simplified it. That's what I need to plug into, right? Okay, so let me go back here. Sorry about that. Okay, I'm actually plugging into, what I'm plugging into is cosine squared theta minus 1 plus what is 2 cosine squared theta minus 1 plus cosine theta, right? That's the one we're actually looking into. 2 cosine squared theta. Yeah, that's my derivative. This is what we're plugging into. Okay, so I'm going to plug in pi over 6. Cosine of 30 is root 3 over 2 squared minus 1 plus root 3 over 2. So that's going to give me 3 halves, right? Because it's, yeah, 2, but then that's how I get 3 halves. So it's going to be 3 halves minus 1 plus root 3 over 2. So this is 1.5 minus 1 plus a positive number. That's going to be positive. Okay, you can use a calculator to verify this. Now, if I plug something like, let me say theta is 70 degrees in here. Okay. This is going to give me okay, so cosine of 70 degrees squared times 2. This is going to be 0.24 minus 1 plus cosine of 70 degrees again is going to be 0.34. So this is going to be negative, right? Less than 0. So that means this is negative. Okay. Increase, decrease, so we have a max here. Now, here's how I can actually get around this, where we don't have to do this. Let's do our second derivative for this one. Okay, so remember our first derivative, I have it here. That's what our first derivative is. Of course, it had a 25 in front of it, right? So our second derivative is going to be 25. And derivative of, let's say, cosine squared theta, that's going to be 2 cosine theta times derivative of cosine is negative sine theta, right? And derivative of negative 1 is 0. Derivative of cosine is going to be negative sine theta again. Okay, so if I simplify this one now, so I can factor sine theta out, right? So it's going to be 25 sine theta times, so I had, it was 2 cosine squared theta, right? So that's going to be 4, because the derivative do 2 times 2, it makes it 4. Okay, so I have 25 sine theta and then times 4 cosine theta plus 1. I'm going to factor the negative from the sine also. There you go. Now that looks better. Okay, and this is always going to be negative now, right? Well, right? Because between 0 and pi over 2, that expression, sine is positive, cosine positive, so there's negative in front of that. That makes the whole thing negative. So we can say this is always less than 0. So that avoids all of this. See that? So you don't have to pick a test point and all that. But this only works if the second derivative is like always increasing, always decreasing. So you can then ascertain the extrema that way. So this is always less than 0 for all theta in 0 to pi over 2 within our domain. So therefore, because it's less than 0 by second derivative test, by our second derivative test, theta equals pi over 3 will maximize the area. Okay, so we have the answer to the question. Therefore, what should the angle be to maximize the flow? Theta has to be pi over 3. Okay, so again, there is a way to avoid using first derivative tests if it's kind of messy. And that concludes this exercise. Okay, let's take a look at maybe one last one. Okay, let's take a look at this last exercise. In this exercise, we were given during daylight hours, some birds fly more slowly over water than over land because some of their energy